All right. So as I was just saying, this lecture will probably be a little bit short, kind of like yesterday's. When it comes to roots and radicals, it's far less tedious than what we've been working on so far. So I definitely encourage you to go back and study systems of equations. If you're kind of like getting done with this really early and this seems easy, go back and study systems of equations, because we do have the next exam that's going to start popping up. Also, now might be a good time, if you've got any extra study time, to start kind of like reviewing stuff that we did at the beginning of the semester, because the final is cumulative. One of the best ways to study for the final is to basically do all of the exams that we've done so far, kind of like do them on your own and see if you can complete those. If you can complete all the exams we've done so far, you should be okay on the final, because the final, it's just a compilation of all the exams we've done so far.
How many questions?
What's that? The final's got 15 questions, and you still get to cross one out. So there's a few more questions than on the normal exams, but not that many more. And it's all the same rules for the final. I believe our final's scheduled on Wednesday. No, definitely not next Wednesday. No. So next week is Thanksgiving. The week after Thanksgiving, we'll come back and take the exam. And then at the end of that week, we'll start prepping for the final.
Okay. Next Wednesday? It says next Wednesday.
No, not that soon.
Wednesday is chapter 7 and 8 exam. So next Tuesday is chapter 7 and 8 review. Next Wednesday is chapter 7 and 8 exam. Next Thursday is final review.
You're like, oh.
Oh crap, wrong day.
Yeah.
Here, Louis.
Is this the updated one?
Yeah.
Yeah. Let's see. What do we got? So we got
Put it in your calendar.
8.2, Tuesday, 8.3, 9.7.
Following Wednesday.
I thought it was Friday.
No, that's
That was
what
Friday too.
How was it?
we're not.
I was like, oh shit, it's Thursday.
Yeah,
So
we're on schedule. Yeah, so next
We're
week
okay.
we're gonna keep reviewing chapter 8,
Yeah.
and then when we get back from Thanksgiving break, we'll have one day of review, and then we take the exam.
Yep.
Yeah, and then we start right in on the final review.
Oh, no.
Yeah, that like last week is a little bit brutal, and that's why I kind of like. I'd say, if you want to start studying now, it's probably a good idea, especially if this stuff is sinking in pretty quickly, which it usually does if you do some repetition with it. And so if you find yourself with a couple of extra hours this weekend, it's always good to just go and start reviewing the early stuff again.
Don't suppose you have those printed off somewhere.
No, but I can print them off if you come to my office. Yeah, and I also have, not only do I have those, I have all like the practice packets that I send you guys home with. So just let me know what you want, and I can print them off at my office. Yeah, I can honestly, I can probably do quite a bit of that. So, okay, so let's go ahead and start this chapter finally.
We only get one card for the exam.
Yeah.
Seriously?
Yeah, you really shouldn't need any more than one card. Like you might put like your graphing formulas on there and a few of your word problem formulas, but really besides that, there's like exponent rules, I guess. It's front and back. But yeah, next semester you won't get any card. So it's kind of like, I don't want to like give you too much. And make sure when you make your card, be careful. Okay, so let's start on 8.2. So we went over the basics of square roots yesterday. Do you guys remember what a perfect square number is?
Yep.
Yep, it's just, right? It's an integer squared. 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, and so on and so forth, right? These perfect square numbers are going to be really important in stuff that we're about to do. Okay, so the product rule for square roots basically says that when you multiply two roots together, you just combine them under one square root, right? You don't have to have any like terms. There's no special rules to this. You just combine them, and you can also reverse that process. You can pull two factors apart as well. So for the first couple examples of that, right, I have root 5 times root 7. This is just equal to root 5 times root 7 which is root 35. Root 6 times root 6, that is root 36, which is just equal to 6. Right? So it's just, basically it just says, yeah, if you're going to multiply two things underneath a square root, you put them both under the same square root. And remember, just like in previous examples where we were able to do this, we can go in the reverse direction too. We could pull root 36 apart and make it into two root 6s if we wanted to, which we will later.
I see fractions.
You did see some fractions, didn't you? Boom. I see fractions. All right. So the same thing applies when you're using fractions, right? Two fractions underneath a radical, right? We just put them both under the same radical. 2 over 3 times 7 over 5.
I don't even know how to write this properly.
It's just like a huge check mark.
It's a really ugly check mark.
It is. You'll get better at them. You'll get better at them. As you can see, I've gotten really great at it. All right. So with this one, right, we're multiplying fractions. So we multiply straight across the top and straight across the bottom. So this would give me 14 over 15. When we start adding variables in there, that doesn't change anything. I'll slow down for a second. I've been going a little fast. Sorry. Sometimes I go a little fast on these. So these examples, you can see the variables are in there. It's not going to change a thing, right? We just multiply everything together and put it all under one square root. 2 times 3 is 6, and then I have an x and a y. And just remember to make sure that your little square root sign extends over all the things that belong in there, right? Don't shorten it. Okay, last example, right? Just because the fractions contain variables, that doesn't change anything. Yep, 3y over 11x, right? Yep, variables should not freak you out in this.
Nope, just can't write it properly.
Nope. Can't do it.
It's not happening.
Takes time. It takes time.
Okay. Sorry, my hand is not catching up.
When I was in calculus, I practiced the integral symbol like hundreds of times because mine was like super ugly. It still is not pretty. It's better than it used to be though.
It looks like a hookworm.
Yeah, and then there's like the summation symbol. This one's really weird. I have to practice this one. But yeah, this is math. You practice the weird notation.
I still feel like a bunch of Roman people sat around and decided we're going to just draw weird crap and
right?
people for thousands of years.
Wouldn't that be funny if like our language was the first one, so all this stuff was just like, well, that's an E to us. Everybody else is like, what is this crazy summation stuff? What the heck is a mu? All right.
We said, what the heck is a mu when we first looked at it?
I love mu. I love it so much because you guys have the exact same reaction that I had when I first saw mu. I just like that. I think it's funny. Yeah, like.
Where do you use it?
So I use it all over the place now. Like once you get into calculus, mu is all over the place. It's like a really common term, especially like, what do they use it in?
It sounds like something a cow makes.
A lot, like in differential equations. Yeah, no, there's all sorts of stuff like that. Like, there's like lambda. There's, what else was there? Yeah, right? There's just all sorts of strange Greek letters. And once you get into higher mathematics, the variables, there's so many of them, they use specific ones. Yeah, and I remember looking over at the person next to me, and she was like, like we were kind of partners in crime when it came to math, and she was just like, what the heck is a mu? Except for she didn't say heck. Like, it's not like we're sitting there in class like, I don't know. Why did he just use that? Yeah. Okay. All right, so remember, like I just said, that multiplication rule can be completed in reverse. And so we can start out with two factors, a, b, underneath a radical, and we can split it up. Radical a times radical b. So observe this example down here with root 50. this is how we will be simplifying radicals. So I start with 50. I break 50 off into two factors. One of those factors I know is a perfect square, right? Remember I was telling you guys about the perfect squares. It helps to be able to recognize those. One is a perfect square, so I break up my radicals, right? The one that's a perfect square, I can simplify it. So I do, and that's it. 5 times root 2. And so basically, like, you know, what we're looking to do is we're looking to simplify perfect squares in this chapter. That's pretty much all we're doing in a few different ways. So with that being said, we'll introduce this definition, which is in your books. You don't need to write the whole thing down. But it says the simplified form of a square root is it's simplified when its radicand. Remember, the radicand is the part underneath the radical sign. When its radicand has no factor other than 1 that is a perfect square. So when we say like root 2, there's no perfect squares in there other than 1, so that's fully simplified. If I say root 7, there's no perfect squares in that, so that's fully simplified. If I were to say, however, if I were to say, let's see now, 28, I would say, hey, wait a minute. 28 contains a 4. That's a perfect square. I'm going to rewrite this as the square root of 4 times the square root of 7. The square root of 4 simplifies into 2, and so now I have 2 roots 7. Right, and so that's the basic of what we're going to be doing here. Sometimes it happens with variables, sometimes with numbers like that. And the way you pronounce this, or the way that I pronounce this, I guess, and the way that my instructors used to, you say 2 roots 7. You could say 2 times the root 7 if you want, but it seems a little more smooth to say 2 roots 7. Okay. So back to the main stuff. So once again, just notice that all we're doing here, we're simplifying perfect squares. That's it. Anything that is not a perfect square, we leave it. Okay, so 18. Everybody, yeah, somebody just said 9, right? We could split it up into 6 and 3, but neither of those are perfect squares. So we use 9 and 2. Root 9 times root 2. And then on the next step, I simplify the root 9. So I have 3 roots 2 here. Okay, if you want to check your work on this, you can just compare answers, right? You can enter right into your calculator, root 18. So let's see now, root 18. Enter. That gives me some crazy number that starts with 4.2426. Then I'm going to enter this one, 3 times the square root of 2. 3 times square root 2. I get the same number, which means I'm correct. Okay, and it doesn't necessarily mean you're fully reduced, it just means that you haven't changed the value, okay? So you might have to reduce more if that's the case, but you haven't changed the value, so that's an indication you're on the right path. So this next example, this one, pay attention to this one. So this one here, notice I have 2 different variables. One is a perfect square, one is not. Right, so I follow the directions that I put up here, right? If you have a perfect square, you simplify it. If it's not a perfect square, you leave it under the radical. So I break this up into the square root of a squared times the square root of b. And then on my next step, the square root of a squared just turns into a. So I have a roots b. Uh-oh. And this is kind of a step that you'll be doing on the more complicated problems, is like this step right here where I sort of just, I wrote stuff that's a perfect square, and then I separated it from stuff that was not. Right? You get used to that. We'll be doing that on most problems. So on this next example, I have a 196. I don't know. It'd be nice if this had an even square root. I don't think it does, though. It does. All right. So the square root of 196 is 14. So we don't even need to do the thing where we pull out a perfect square factor, because 196 is a perfect square. So we rewrite this stuff as square root of 196 times the square root of t squared, because that's a perfect square too, and then the square root of u. And I know that u is just going to stay out there because it doesn't have a perfect square. So I can see now this thing will simplify and this thing will simplify because they're both perfect squares. This turns into a 14. This turns into a t. And then my square root u just stays there. So here's my final result. Okay, here's an example of an evaluation problem for a square root. And this one's particularly relevant. I'll explain why in a second. But suppose you were given these values to plug in here, right? B equals 6, C equals -5, and A equals 3. And it says evaluate. That means I plug them all in and calculate. So this gives me 6 squared minus 4 times A, which is 3, times C, which is -5. Okay, and so when I do this, I just take it one step at a time so I don't mess anything up, right? As you guys know, I like to mess stuff up. So 36 minus, there's a double negative, so it'll be a plus. 36 plus, is it 60? Nice. Good. All right, and that gives us root 96, which I don't think has an even square, does it? We should definitely simplify that, though. So let's see now. Does 96 contain a perfect square? So this is how we handle it when we have no idea, right? Suppose I have 0 idea. I could probably try and divide this by 4 to start out with, but suppose I didn't know at all. So 96, I do my factor tree, right? So 96 divided by, it is divisible by 4. So we know it contains at least one perfect square, right? I create my factor tree now. So if it's not prime in a factor tree, I draw 2 branches off of it, and on the end of each branch, I put a factor. If it's prime, it just drops straight down. So the 24 breaks into 4 and 6. The 2's drop straight down. The 4 breaks up into 2 2's. And the 6 breaks up into a 2 and a 3. So now, after you've finished your prime factorization, you circle any pairs that you have. Pair of 2's, pair of 2's. Multiply everything that you've circled together. That gives me 8. No, that gives me 16, sorry. I was like, wait, that didn't work. That gives me 16, which is a perfect square. And 16 is multiplied by whatever you had left. This is just a 2 times 3, so 6. All right, and so when I simplify square root of 96, I'm going to break it up into these 2 factors. Root 16 times root 6. Root 16 simplifies to 4, and so I have 4 roots 6. Okay, so yeah, if you're at a loss and you have no idea, you can do a factor tree and you can circle all the pairs on the bottom. Or you could just start dividing by perfect squares if you want to do more of a brute force thing. I gave you the list of the first 50. All right. And one more thing. This is something that you won't be tested on, but this is just something that might help you probably next year, not even this year. This polynomial, 3x squared plus 6x minus 5. This polynomial and this right here, this is a formula to tell us if this polynomial is prime. If this formula comes out with a negative number under our radical, that means that the polynomial that we entered in is prime. Right? See how over here I have a equals 3, b equals 6, and c equals negative 5? And you'll learn why that's true next year. But it's just an interesting relationship. If this little thing underneath the radical ends up negative, whatever polynomial you've got is prime, because it produces an imaginary number. Don't worry, you won't be tested on that though. It's just something that you'll be able to use next year.
Just write it down.
You won't be tested. No, yeah. It's going to be super helpful for you if you recognize that, like next year when you start getting more prime polynomials. But they'll teach it to you again. All right. So let's talk about simplifying square roots of powers. We already did a little bit of work on this at the end of yesterday's class. And as you guys might have remembered, the basic rule is when you have an even power, it splits in half when you simplify it. This is why. Because when we have something like x to the 10th, we can rewrite that as x to the 5th squared. Right? Yeah. And this is like our magic setup, right? When this happens, the thing that's inside the square just pops out. X to the 5th with no square root and no squared. Right? And that's going to be, I would like to see this intermediate step, especially during like this section. On the final, it might not be as big of a deal, but you know, I would like to see something like this intermediate step. So when we have an odd power, all we need to do is split off 1. And so we rewrite this as x to the 10th, root x to the 10th times root x. We know exactly how to simplify x to the 10th because it's a perfect square. So I can rewrite this as x to the 5th root x. And notice this is the pattern whenever you have an odd numbered exponent. Right? You'll end up having that exponent minus 1 divided by 2 out front, and then a single factor of that inside the square roots. Okay, so even number, rewrite it as a square and split it in half. Odd number, split one factor off and then just simplify the even root. All right, so let's try this. X to the 6th. How can I rewrite this?
X cubed squared.
Good, yeah. X cubed all together squared, which means I get an x cubed out. Suppose I have p to the 12th. I can rewrite this as p to the 6th squared. No. And so this thing all on the inside of the square and the square root, that's what comes out. P to the 6th. Once again, z to the 22, I recognize that's an even number, so I just rewrite it in terms of squares. Z to the 11th squared, and z to the 11th pops out. By the way, when you get into like the larger problems that you'll probably see a little bit on this homework, but when you get into the larger ones that have like 5 or 6 variables, like, you know, this step is less necessary, right? Like I want to see your work when it's a really basic problem like this, but when you've got like 5 or 6 variables to deal with, this might just make your page a little crowded. So it's okay to leave that off if you don't like it. Okay. So now we've got we've got an odd exponent. So first thing I do is I break one factor off. That gives me x to the 8 times plain old x. X to the 8 can be rewritten as x to the 4th squared, good, times root x. So then on the next step, I just say, okay, I have x to the 4th inside my squared. Good, perfecto. Right, and once again, right, we started out with 9. 9 minus 1 is 8. 8 divided by 2 is 4. So here's where we ended up here, and we've got one factor of x hanging out. Okay, so here's another example of when we have numbers and variables mixed in here. Except for this one, the number is not a perfect square. So on this one, let's see now, 32 divided by 4 gives me 16, isn't it? Yeah, so 32 is 16 times 2, right? Yeah, I need you guys for this. So we can split that off. And watch how I do this. When things need to be simplified like this, I'm just going to deal with them one at a time, right? And so I'm going to deal with the coefficient first. The 32 splits into root 16 times root 2. Then, this p to the 19th, remember it's an odd power, so I need to split one off to create an even power. So this one gives me, p to the 18th times root p. So now in this step, I go through and I say, what can I simplify here? I can simplify this, and I can simplify this. So that's what I write out front. 4p to the 9th. Right? And notice how on this step I skipped that intermediate, right? Because this is a little bit larger of a problem, and there's no reason to get your paper too cluttered up. So now that I simplified those two things, I cross them out, and then whatever's left, I rewrite it all under the same square root, 2p. Excuse me. So be very careful. This is a really common thing to do. It's super common, and I think I probably do it myself sometimes, is when I see the square root of x to the 9th, I think, well, the square root of 9 is 3, so I'm going to call this x cubed. No, don't do that, right? Remember, we're not square rooting the exponent, we're square rooting the number of x's. Sounds kind of strange. All right. So remember, we always try and simplify as much as possible, and sometimes multiplying two of the roots together will make them simplifiable, I should say. All right, and we notice that that's going to happen here because here's a factor of 2, and we also know that 14 contains a factor of 2, right? So there's going to be a perfect square when we put these together. So 2 times 14 gives me root 28. And I think we did this one earlier, right? It's 4 times 7. That's 28. 4 is a perfect square. So I rewrite it as root 4 times root 7. And that gives me 2 roots 7. All right, on this next example, you can actually predict these a little bit, right? You can see 5 doesn't share any factors with 6, does it? So that number is probably not going to simplify after we multiply it in there. So when we multiply these two things together, we end up with 30t squared. 30 doesn't contain any perfect squares. If you want to, let's just check, right? If we didn't know that ahead of time, we could do our factor tree. 30 equals 2 times 15. 2 is prime. 15 equals 5 times 3. And we get to the bottom here and we notice there are no pairs, right? Which means there are no perfect squares. So the 30 stays the same, but I do split off my t squared. I notice that's what I can simplify, so I write it out front. And so, yeah, something just to pay attention to, something that's a really common mistake, but not everybody makes it. It just seems to pop up more often, is that people are nervous about when to remove that square root. So when you move from the square root of something squared down to just that thing itself, all that stuff goes away. Okay, so don't be too tempted to drag that square root down with it after we've already simplified. Not saying you would have done that, but a lot of people do. Okay, next example, square root of n squared times the square root of n cubed. Remember, we just multiply all these things together, n squared times n cubed. All right, we just need to remember our rules of exponents for this. We add these exponents together. So this gives me square root of n to the 5th. Now to simplify square root of n to the 5th, remember, we rewrite it and we break one factor off because 5 is an odd number and we need an even one to simplify. So we rewrite this as n to the 4th, an even number, times that single factor of n. And then finally, I can rewrite square root of n to the 4th as square root of n squared squared, which means I'm allowed to pull this little part in the center out. Okay. Okay. Any questions so far? No, it's not too bad, and some of the stuff in the homework will probably throw you a little bit, like it usually does. Like I'm pretty sure I don't ever quite cover the homework like it's gonna appear, but yeah, it's not too bad. So on this next example, right off the bat, we're gonna multiply all these things together. So this is going to give me 2 times 9, which is 18, and then x to the 8th times x cubed, which is x to the 11th. So now when I look at this, I know that I'm going to need to just break these things apart and simplify them separately.
What's the little x to the x? What is that?
11. Sorry. And that's just because I had 3 here and 8 here.
Sorry, I just couldn't see it.
It's all good. Oh yeah, I wrote it just as small as possible, didn't I? I totally did. Look at, there we go.
Really far back here, I'm like, what is that?
That was a tiny
Tyler,
11.
I know you're watching this at some point. It looked like a little squirrely little blob. So, continue.
Right? Where is Big Papa today? All right. So now, remember, I split off the numbers and the x's and do it separately, and I see that 18 will split off into 9 times 3. Sorry, 9 times 2, and 9 is a perfect square. So that's what I want to split off. So root 9 times root 2, and then my x terms, those also need to be split up because I need an even number of exponents before I can simplify. So I rewrite x to the 11th as root x to the as the square root of x to the 10th times the square root of a solo x. So now at this point, the things that I can simplify are a little jumbled up, so I make sure that I recognize what's going to be simplified here, this and this. Now I write it out front. The square root of 9 is 3. The square root of x to the 10th is x to the 5th. And then the stuff that can't be simplified just gets included all underneath the same square root, 2x. Okay, so let's just do a few examples and then we'll call it a day. Just a few extra examples that are maybe a little bit weird. Yeah, so we haven't really done any large numbers yet. This one's actually an easier large number than most because you might be able to recognize that, well, 500 is divisible by 100, which is a perfect square, right? Yeah, so we don't necessarily need to draw out the tree or anything like that. We just rewrite this as the root of 100 times the root of 5. Yeah, and that turns into 10 roots 5. That's okay. I'll recognize it and chuckle. All right, so with this next root, the m's just a solo m, so that can't be simplified at all. The 40, that's equal to 4 times 10, right? 4 is a perfect square, so that's what we're going to factor out. So I'm going to split this off into root 4 times root 10m. And you could separate the m at this point too, but there's no real point because it's not going to simplify, and neither is the 10. So now I simplify my root 4, that gives me 2, and that's 2 roots 10m. Okay, 20b to the 7th. Yeah, I think I heard somebody say 4, right? And that's something that, with a little bit of practice you'll get better at, is recognizing perfect squares. But for me, like if I'm ever really in doubt, I usually just punch in the calculator and see if it's divisible by 4. It's like that's usually the one that it is, so I'll just try that one out. So this one, so I rewrite the 20 as root 4 times root 5. And then b has an odd numbered exponent. Yeah, so we have to split one factor of b off. So I have root b to the 6th times root b. Now I go through and I see everything that's a perfect square that I can simplify. The square root of 4, that's just equal to 2. The square root of b to the 6th, that's just b cubed. Right, remember 6 is an even number, so we just split it in half. And then everything else cannot be simplified, so it just goes under the same square root. This next example, I think, is just boring. Sorry, I don't know why that's even in there. That's a super boring example.
Super boring.
It is.
Might as well just jump past that and go to the 90x.
I think I will, yeah. I don't like, that's lame. Okay. So yeah, let's tackle this guy.
So row.
All right, so this one has 3 different things that we need to consider, right? So this problem's going to get a little bit bigger. So first of all, we have our 90. Let's see now. Does 90 contain a perfect square? I think it does. Is it 9? Yeah, it's definitely 9. Okay. So I rewrite this as root 9 times root 10. Then I consider my x's, right? Yeah, that's an odd number of x's, so I need to break one factor off. X to the 4th times plain old x. Right, and then my y, that one, it's even already, so it's kind of already set up for me. So I'm just going to write it back here, y to the 10th. Just like I did with the other problems, I go through and I make sure that I know which ones I can simplify, and then I write those out front. 3x squared y to the 5th. Good. Yeah, because that's all that we have left. So it goes all under the same square root. And we just have a 10x there. Boom. Okay. You know, I'm sure you guys can guess what's about to happen here. So it doesn't change much. Just because there's 4 variables, we don't change anything, right? We break them all off and consider them separately. R squared, that's easy, right? That's an even number, and it's already a perfect square. So we can just write that out front. X cubed, that's an odd. So we've got to split off a single factor. X squared and plain old x. Y to the 4th, we just write that as y to the 4th, or y squared squared. Yeah, let's do that. Right? Don't forget that that's the step that we're skipping, right? Okay. Then we have z to the 5th. Yup, you got it. Z squared times a plain old factor of z. Okay. Go through and say, what can I simplify here? This. 4 things. So the r squared turns into a plain old r. X squared turns into a plain old x. Yup. Y squared and z squared. Yeah, and then everything else just goes underneath the root. And we're done. Yeah, so those, you know, they can get a little bit expansive like that, but as long as you keep things organized and kind of like keep your algorithm straight, it shouldn't be too much of a problem. Any questions about this stuff? No? All right. Well, thank you for your patience, guys. And have fun. And remember, start studying a little bit.